Hello, future elementary school teachers. Welcome to your Friday pre-recorded lesson. We're going to talk a little bit today, just kind of introduce integers and take a look at some of the preliminary properties and representations that might be helpful as we start to talk a little bit further about some of the main operations with regards to integers. So let's just refresh our memory on what the set of integers looks like. So the set of integers essentially contains all of the positive and negative whole numbers. So it contains all of the whole numbers. And then it contains what we call all of the opposites, which would be the negative numbers. It also contains the number 0. Okay, so we usually use a kind of one of these fancy Zs to denote it. That comes from the German word for numbers, I believe, Zahlen. And yeah, so this is our set of integers. This is the set that we're going to want to be working with in this particular lesson. And just a couple things to note here. So essentially we take the natural numbers, or the number set we've been working with so far, and what we're going to do is we're going to add to the natural numbers what we call the opposites of those numbers. There's a bit more of a mathematical term that goes along with what we mean by opposites, but the idea is since 2 is inside the set of natural numbers, I want the opposite to be inside the set of integers, the number -2. So all of those kind of reflected or mirrored numbers across 0 are going to end up being inside of the set of integers. Now all of these opposites, we technically call them the additive inverses. That's the math term that goes along with these numbers. And we'll get there in a second. I'm trying to think, is there something else? 0, yes. Yeah, and essentially the reason we think about the set of integers is we would like this particular set of numbers to be closed under the subtraction operation. So this is why the set of integers were essentially created. So recall that when we were thinking about our natural numbers, this set was closed under addition and closed under multiplication. But it was not closed under subtraction. I couldn't take any two whole numbers, subtract them, and always get a whole number. And it wasn't closed under division, right? I could also possibly get remainders when I'm working with the division operation, in which case we're going to be getting things like fractions or decimal numbers when we go to do division. So for the set of integers, we essentially add all of the opposites into the set, and this allows it now to be closed under the subtraction operation. Now the set of integers still isn't closed under division. So to solve the closure under division problem, we're going to see probably next week or the week after that we create this new number set, the set of all fractions, that solves the closure under division problem. So yeah, just a couple kind of interesting, I think, preliminary notes here about why we care about the set of integers. So let's talk a little bit about some of the other properties other than closure. Of course, the set of integers like addition and multiplication are still commutative. And addition and multiplication are still associative within the set of integers. Subtraction and division are still technically going to be a bit of a problem. They're not going to be commutative and they're not going to be associative either. So it doesn't really matter what set we're working with. So we still have that the number 1 is the multiplicative identity. And we still have that the number 0 is the additive identity. Okay, so that is still truthful inside of the set of integers. And maybe a new property that we have with regards to the integers is having this idea of having an opposite number. Okay, in math terms, we call the opposite of a number the additive inverse. So an additive inverse is a number that I can add to an original number to get to the additive identity. So it's kind of like asking the question, given a number, what can I add to it to get to 0? So that's the question we ask in order to find the additive inverse. So for instance, let's play a game. The final answer we want is 0, and I give you the number 2. So you need to scan through the set of integers, and you need to find a number that I can add to the number 2 that's going to get us to the number 0. And of course, hopefully you all know that that is the opposite of 2, which is negative 2. Okay, so we say that 2 and negative 2 are additive inverses of each other. Now, if you want to get super technical about it in your elementary or middle school class, you can use the terminology additive inverse, but I find that students are very receptive over the term like opposite or mirrored number. Like they usually, and sometimes the textbooks will use other kind of terminology to talk about the additive inverse just to make it a bit more accessible. I do like the word opposite. I think that carries a lot of meaning in this particular context. So opposite, you'll hear me use that word probably quite a bit. So obviously, if I start with a positive number, the negative number that corresponds with that's going to be the additive inverse. If I start with a negative number like negative 5, obviously the number that I would like to add to that is the positive associated number. And then the one kind of special case is that if we start with the number 0, what can we add to the number 0 to get back to itself? Well, we have to add the number 0. So 0 is the only special case. 0 is its own additive inverse. It's its own opposite. Okay, in other words, 0 and negative 0 are essentially the same thing. Okay, so it doesn't matter if I have, a plus sign in front of 0 or a negative sign in front of 0. I always interpret that as just the number 0. So that's kind of maybe a new special property. I think we had talked about additive inverses before. But yeah, just maybe a little refresher on that terminology. Okay, so we talked about closure, we talked about associativity, commutativity, talked about inverses, talked about the multiplication identity. We're doing pretty good. So just the distribution of addition over The distribution of multiplication over addition and subtraction is still true. So multiplication can still be distributed through a set of brackets over addition or subtraction. So for instance, if I had something like -2 times, I don't know, -7 plus 3. All right, so if I had an expression like this, I mean, I obviously could go through the order of operations. Maybe we'll do this in 2 ways so you can kind of see what I mean. So when I'm working with just numbers like this, most of the time it's easiest just to use the order of operations, in which case we will do this addition first. -7 plus 3 is equal to -4. And then we would multiply -2 and -4 together to get +8. And we are going to talk a little bit about addition and multiplication like this and why the signs change or don't change. I think that's going to be kind of a core part of our conversation at the end of the lecture today and on Monday. But I do want you to notice that, like that's kind of the standard way we might solve this thing, but it is possible to also distribute the -2 through the brackets and end up with the same final answer. So distribution says I can take this number and I can multiply it to both of these other numbers to get something that looks like this, -2 times -7, keeping the addition sign, and then getting -2 times 3. And then simplifying this resulting expression. So -2 times -7 is equal to 14. And -2 times 3 is equal to -6. So now I have 14 plus a -6. This is really like saying 14 take away 6, which gives us the number 8. So this is what we mean by the ability to distribute. I can either kind of go through the order of operations procedure to get to the final answer, but if I wanted to, I could distribute this multiplication across the square brackets, simplify, and also get the same final answer. Okay, I think that deals with most of the big properties of the integers. So let's take a moment to chat a little bit about one of the representations. Now, one of the most common models I've seen to introduce integers is the chip model. And in the chip model, we have basically like a 2-colored object. I don't think I have anything here at home, but we have like maybe a square or a circle, and on one side it has one color, and on the other side it has a different color. For the purpose of our notes, it's probably easiest for us to maybe use just like circles, and then we're either going to color it in or we're not going to color it in. So ideally we have objects that have a color on one side and a different color on the other side. Maybe that have different colors on each side. And the idea is that we let one of the colors represent the positive number, and we let the other color represent the negative of that same number. So let's say, for the sake of argument here, I'm going to use, let's say, white and black. So white is going to represent a +1, and black is going to represent a -1. realistically in real life, I'd have an object that I could kind of flip over to represent these plus or minus ones very, very easily. So if I wanted to represent some integers, I could do the following. So let's do a couple examples. So let's do A, let's do, I don't know, -4. B, let's do +3. And that should be good. I think you guys will probably get the idea here. Of course, with -4, I just draw 4 circles, right? I have 4 objects, and we're going to say that all 4 of those things are negative. For +3, again, we want 3 objects, and we're using the white color here to represent a positive number. Now, with integers, when using this model, we have this idea that we can create what are called 0 pairs. So I know that 1 plus a -1 is equal to 0. So what does this mean? This means that if I had both a -1 and a +1 beside each other, this is really equal to 0. So any model, any chip model that I have, I technically could add as many blacks as I wanted to, provided that I also add the same number of white chips. So this is the idea of a negative pair. And it allows us to have many different representations of the same integer. So, for example, we know that this is -4. But we also know by the 0 pairs property that this is also -4 because, I'm just going to circle in red, because this is 0. And if I wanted to go even further, I could add more 0 pairs, right? So this should also be -4 because I know that all of this is 0. So this is what we mean by negative pairs. It gives us flexibility to model our integers in some very interesting ways. And it allows us, I think, in very kind of small case scenarios to really explain what's happening with addition and subtraction. So I think what I want to do just to kind of finish up the discussion today is to utilize the chip model to do a couple of questions with regards to addition and subtraction. And then we'll kind of dive into how we might work with some larger numbers working with integer addition and subtraction on Monday. So let's look at maybe a couple different cases. And we're still going to use our same standard representations for addition and subtraction. So for addition, we'll model both of the addends, combine everything, and utilize the 0 pair property to kind of cancel out stuff. And for subtraction, I still want to think about the takeaway model. That's a very strong model to think about with regards to subtraction. So maybe let's just write that down. So addition, we're still going to use so 1 for addition. it will still be helpful to model the add-ins. And then use the zero pair to kind of cancel stuff out. And for subtraction, we still want to use the takeaway model. So we're going to model the minuend. And then we'll try to utilize the takeaway model. All right, so let's take a look at a couple examples. Let's try a nice kind of straightforward addition kind of question. So let's do -5 plus 7. How could I try to motivate that -5 plus +7 is equal to +2? You know, how do I motivate that using the chip model? Well, we want to model both of these minuends. So we're going to model our -5 using our black chips. Okay, and we're going to model our 1, 2, 3, 4, 5, 6, 7 with our white chips. And then what I'm going to do is I'm going to go through with a red pen and I'm going to cross out 0 pairs. So for example, this -1 here is going to essentially cancel. It's going to be added to get 0 with one of these positive chips. So we can kind of go through and remove our 0 pairs. So if I actually had a model, I could actually just remove these pairs one at a time from the model, and we're going to see that we're left over with 2 positive objects. Okay, so that tells us our final answer here after removing our 0 pairs is going to be +2. What if our negative number happened to be larger than the other number? So if the negative number is larger, in this case the -7 is bigger than the +3, the absolute value, right, like the actual length of these numbers. So I'm going to be left over with a negative kind of number at the end. And again, I want to try to use the 0 pair property to motivate why our final answer should be -4. So again, it really just comes down to this understanding of modeling those add-ins. So here I'm going to model -7, and I'm going to model +3, and then we're going to start removing our 0 pairs. So one of these will add with one of those to get 0, and one of these, and one of these, and one of these, and one of these. So after we've simplified, we see that this addition should give us 4 black chips left over. Okay, so after simplification, I see that I get -4. And so what we really want to do with our students is we don't want them to be modeling these kinds of things with chips all the time, although that's a nice fallback to be able to model things with. What I would like is to develop some kind of more generalized procedures. So if I have an addition like this, what we usually do is look to see which number is bigger. And I'm using bigger a little bit loosely here because I think, you know, when I look at this expression here and I'm comparing -7 and 3, I mean, technically +3 is bigger because it's more to the right of -7. But what I'm really doing is I'm really trying to analyze the absolute value. I'm trying to figure out how far away are these numbers from the origin, from the number 0. -7 is 7 spaces away from 0, and 3 is only 3 spaces away. So the -7 is going to have more of a pull on where our final sign is going to be than 3, because -7 is further away from 0. So if I'm thinking about this on a number line kind of perspective, when I start at -7 and I add 3 to that -7, I don't cross over 0 because I'm so far away from the number 0 that it's impossible for me to land on a number that's a positive number. So this is what I mean by kind of analyzing which one is bigger. We're essentially trying to figure out which one of these is further away from 0. and then realizing that the sign of that number technically is going to be the winner, right? So looking up here, I'm comparing 5 and 7 because 7 is further away from 0. It's going to be the winner of this addition competition. So the sign of 7 is going to win. I'm going to get positive 2 instead of a negative 2. So that's how we kind of think about addition. That's the generalized rule, and we'll come back and we will revisit that a little bit on Monday. But maybe worthwhile for us to maybe just to jot that down. So the general rule for addition is 1. We want to see which number is further away from 0. Okay, once you've decided which number is further away from 0, the sign of that number is going to be the sign that we have in our final answer. And I actually need to be a little bit careful here. There's actually a couple of different cases for addition, and I will kind of flesh out all of those cases on Monday. And there's 4 different cases. I could be adding a positive number and a positive number, in which case it's regular addition. I could be adding a negative and a positive number, in which case this general rule kind of applies. And then we could be adding a negative number and a negative number. And again, I think the general rule is going to apply here as well, but the subsequent step, like the secondary step, is going to be a little bit different compared to, a little bit different depending on what 2 numbers we start with. But this is a general rule that does work all the time, right? Look at your 2 numbers that you're adding together, determine which one's further away from 0. That should be the winning sign. That's going to be the sign that we take for our final answer. And we'll try to flesh out all of the different cases, I think, on Monday. Let's kind of keep on working with some more examples, just so you kind of get a sense, like, maybe of what I'm kind of trying to allude here to. So maybe let's take a couple of negative numbers like this. How could I model -6 plus -3? Well, in this case, we're going to model our add-ins. We have -6, and we're going to model our -3. Boom, boom, boom. We notice that there are no 0 pairs. So this is our final answer. Final answer is -9. Okay, so I don't have to cancel anything out because there are no 0 pairs. So this kind of looks like a regular addition, right? I add 6 and 3, I get 9. 6 is further away from 0 than 3, so it wins the sign war, let's say. So we get a negative kind of number, a -9. And it's kind of, I think, interesting to compare and contrast these two, right? And this is kind of what I mean by you have to be mindful of the interplay between the 2 numbers that you're adding together. If we're adding 2 positive numbers, it's kind of like, regular addition. If we're adding 2 negative numbers, notice that it's also kind of like an addition. 6 plus 3 is 9. We just have a different sign to go along with the 9. But if I'm adding a positive and a negative number, things get a little funky, right? 7 plus 3 is 10. So students kind of get confused there, right? They're going, oh, 7 plus 3 is 10, but why is the answer 4? It's because of this 0 pair property, right? When I have a positive and a negative number, it turns out that subtraction is the way that we have to kind of think about this addition, which is a little awkward. But yeah, we'll really, I think, kind of hammer through all of those different cases on Monday. But you can kind of see those different cases starting to flush themselves out here inside the chip model. So for today, just kind of focus on making sure you're happy with the chip model and that the idea of the chip model makes sense. And then we'll talk about how to apply this to some kind of larger case examples, where, if I have like 137 and negative this and that, like I don't want to have to write out 137 chips. It just doesn't make any sense. So the chip model is only good, maybe for numbers up to like 10, right? After that, you want to develop some other strategies to be able to actually do this work. All right, let's take a look at a couple subtraction examples as well. And again, we'll try to, if we can, develop a general strategy to think about subtraction. So the most important thing here is to model the minuend first. So our minuend here is -6. We're going to go ahead, we're going to model that minuend of -6. Okay, and what the subtraction statement is saying is it wants us to take away -3. Do I have enough negatives down here to take away -3? Yes, we do. Okay, so we're going to circle these. We're going to take them away. And then we're going to see what do we have left over. Okay, so you can imagine if we actually had these 6 negative chips sitting in front of us, I could literally take 3 of those negative chips away and see that the remaining negative chips are 3, right? So I have -3 left over. I have 3 negative kind of chips left. So this is interesting because 6 take away 3 is 3. So it's kind of like an actual subtraction kind of thing here. What happens if we have something that looks like this, though? What if we have -6 take away +3? I think this is an interesting one to compare and contrast. Okay, so what this is saying is start out by modeling our -6. So here's our -6. And what we want to do is we want to take away +3. But notice that there isn't a +3 inside the model. So since there's not a +3 inside the model, we have to introduce it into the model using a 0 pair. Okay, so it's going to change our model to look something like this. We would actually physically add in 3 0 pairs. Okay, so here's our original -6. And I'm going to add in 3 0 pairs. Why do I add in 3 0 pairs? Because now I have a +3 in this picture. This picture still represents -6. This still represents our minuend. But now I have the capacity to take away +3. Okay, so we add in the 0 pairs so that we can take away what we need to, and then we look at what's left over. Okay, so let's take away these 3. And then we have all of these negative chips left over. Okay, so after taking away +3, it looks like we have 9 negative chips left over. And that's interesting, right? Because 6 + 3 is 9. So this is kind of like adding, right? So you can see how students get super confused, right? I think the chip model is nice to help clarify some of this stuff, but definitely having some more generalized procedures is helpful, because up here we did a subtraction and it was kind of like subtraction. But here we did a subtraction and it was actually kind of like an addition. And way back here, we did an addition, it was kind of like an addition, but we did an addition that was kind of like subtraction. So you can kind of get this, like, it's a little overwhelming, I think, when students are first starting to learn integers because they don't know what the hell to do, right? Like, so I would say for now, start getting used to the representation, because I think being able to utilize the representation for smaller integers is very helpful. And it also leads into being able to utilize this for things like algebra too. We have stuff like algebra tiles that we're going to hopefully have the chance to talk about, which are going to follow similar patterns to integers. So if your students are comfortable with base 10 blocks, and if they're comfortable with the chip model, they're going to be very comfortable starting to transition into algebra using the algebra tile models. So this is why the models that I choose to show you are very specific. I think they're specific to the learning outcomes we want to see by, early high school. We want them to be able to be comfortable thinking about things like algebra, right? And doing addition and subtraction with algebra. And it does come down to knowing how to do addition and subtraction with your base 10 blocks, as well as addition and subtraction with your chip models. So let's do a couple more chip models, maybe where we have kind of like an awkward subtraction like this, where we may have to use some zero pairs. And that's probably going to be it for today. So let's see if we can do like 7, take away, I don't know, -4. Okay, so what's that going to look like? Okay, so let's start by modeling our minuend. Here is 7 positive chips, and I would like to take away -4. But I don't have -4 inside the model. So what I need to do is I need to introduce 4 zero pairs, like so. And that gives me the capacity to actually take away these 4 negatives. Okay, so now that I've taken away 4 negative chips, I can look at what's left over, and what's left over is 7 and 4, which is +11. Okay, and one more just to finish off the lesson for today. Let's try -5, take away -7. Again, notice back here, right? 7 plus 4 is 11, right? So this subtraction is actually kind of like an addition, right? Which is so awkward. I find that so bizarre. Okay, again, we'll start by modeling that minuend. So here is our -5. Okay, we need to take away -7. I don't have -7 right now. I only have -5. So essentially what I need is I need to get 2 more negative chips into the picture. So there's kind of 2 ways you can go about doing this. What I've seen students do is just add in 7 zero pairs, and then they're going to have to simplify some stuff. So I'll show you kind of the standard approaches. So one approach is to be like, okay, I don't have enough to take away. Let's add in 1, 2, 3, 4, 5, 6, 7 zero pairs. So this is the long way. Okay, so students will add in 7 zero pairs, and then they'll be like, okay, now that I have enough zero pairs, let me take these away. But now we're stuck with more zero pairs, right? I'm stuck with 5 negatives and 7 positives. So I still have to now go through and kind of remove all of these extra zero pairs. So I've essentially kind of created a little bit of extra work for myself. But after I simplify, I do get to the final answer that I need, which is +2. So that's the long way. The long way is to actually introduce all 7 zero pairs and then take away the -7 portion of that. But then you have to kind of go through this awkward simplifying step at the end. 3, 4, 5. So the more kind of, I would say, clever or the more efficient way of dealing with this kind of subtraction is to say, well, I have 5 negatives here already, so I really only need 2 zero pairs. And with the addition of these 2 0 pairs, now I have 7 negatives that I can take away. Okay, and then we get to our final answer right away of positive 2. Okay, so I'm hoping that that's a good kind of refresher and introduction back into the world of integers. They are a funky set of numbers. So Monday we will try to, maybe we'll do a little refresher on the chip model with a couple examples, and then we will start to really hammer out, I think, some more generalized rules that are going to be helpful, I think, for you and your future students if you have to deal with integers. I think, want to spend a little bit of time next week also going through the order of operations after we kind of deal with the addition and subtraction problem. Maybe we'll talk a little bit about multiplication, right, and why the signs may or may not change when dealing with multiplication. And then we eventually want to get into working with exponents, so a little kind of a refresher on exponent rules and how to think about positive and negative exponents. So that's kind of what's up and coming in the next couple lessons or so. So I will see. I'll have a lovely weekend, by the way. I've finished marking the video assignments, so hopefully that has those marks have been posted for you. And I have just a few more of the drafts of the lesson plans to mark. So I'm hoping that I'll have them done, hopefully, at the latest by tomorrow. So expect most of those marks to be rolling in to you over the weekend. So let's catch up on Monday. Have a good weekend, everyone. And we will chat very soon. Bye.